This talk is about using deep neural. Is it not switched on? Yes. Thank you. Is a proposal of how deep neural networks can be used to solve inverse problems. And so the particular way we want to use deep neural networks is to link them up with very classical approaches to solve inverse problems, which are called variational regularization methods. So this is the rough idea, and where the deep neural network comes in when solving such a variational regularization approach, you will see in a few minutes. I think it's also nice because it links very nicely to what Lars has been talking about in the morning, as well as Armand. Sorry. On the one hand, sticking to the more classical approaches, since we can prove things about them, we have some guarantees on the solution. But on the other hand, we're going to see the particular deep neural networks we're going to use are GANs. So that's how it links to Armand, although I have to say we are in particular interested in the discriminator that he wanted to get rid of. So that's again the difference here. Okay, so let me dive into first showing you what these variational regularization approaches are all about. Inverse problems, in particular I'm interested in solving inverse imaging problems, I should say, are generically encapsulated in this equation here on the top, which means the following. You are measuring data that I call y, but you're not directly interested in y. You're interested in something that is hidden in y, which I call x. And what I know about the relationship between x and y is given by this equation here, namely that before I observe x, it has gone through some forward process, some forward operator has been applied to it. And because we are talking about real measurements, there are always random corruptions in them, and those are just modeled here by this generic noise term. Okay? In most of the examples I'm going to show you, x will be an image, or it could be some information that you want to retrieve from this image, like a segmentation, for instance. And the forward operators, capital T, that could be linear or nonlinear operators, are, in the cases that I'm interested in, very complex. So they're quite difficult operators. In the following sense, in the sense that just having this equation here, the problem of retrieving x from y is in general an ill-posed problem. Ill-posed in the sense that either a solution x to this equation is not unique, if you have an underdetermined system, for instance, or and this actually is the case in most of these inverse problems, that you lack stability in the solution. Which means that although you have measurements y1 and y2, which are very close to each other, we have seen this actually in last presentation, the solution x could be far off, so you don't want that. So how does this variational regularization approach comes in? This approach comes in trying to make this intrinsically ill-posed problems well-posed by adding some additional regularity in terms of prior information you have about the type of solutions you want to compute into the mix. And so instead of now starting out with wanting to solve this equation, I want to compute an approximation to a solution to this equation as a minimizer of an energy that I call J, which on the one hand encapsulates this equation here in what I call here the data fidelity or data discrepancy term, which quantifies your forward model against the measurements in some way. Could be, for instance, just the least squares fit between the two. And on the other hand, now this regularity comes in, also has a regularization term here that is in particular looking for solutions x for whom this regularization term is small. Okay, and how small it should be is determined of how much I'm weighting this. Just think of alpha as a scalar parameter that you choose. Okay. In imaging, so I have here one example in imaging, a very popular type of regularization term that has been used extremely successfully over the last 30 years or so is the total variation, which is given here, which is a particular type of edge-preserving regularization, which gives you solutions that can still have discontinuities. And these are properties that we really like in images. We want to preserve edges. We don't want to blur them out. So this is why this total variation has been so successful. Okay, so this is the classical approach. And let me just give you kind of anecdotal overview of how many applications these variational regularization methods in fact have. And so this is anecdotal in the sense that these are examples that come out of the Cambridge Image Analysis group here in Cambridge. Just to very quickly run over them. So one example could be with applications in forest conservation. There's a collaboration here with the group in forest ecology in plant sciences in Cambridge. And so they are interested in, based on remote sensing data that they collect from airplanes, based on this multi-sensor data, could be LiDAR, hyperspectral imaging data, they want to delineate, to segment individual trees. And so I will not talk more about how this is achieved, but it's also based on a type of variational approaches as we have seen on the first slide. And actually Andrea will speak a little bit more about such approaches in her presentation. This is another application that I like to show, which is maybe a bit surprising. This is an application in art, virtual art restoration. So here, the example I'm showing you here is an illumination from a manuscript from the 16th century. Where this manuscript shows in pictures the creation story, the biblical creation story. And so you have Adam and Eve here and so on. And so what art historians realized is that that the illuminations in this manuscript have been changed over time. And in particular what has been changed is that Adam and Eve got skirts drawn onto them. And so this is something that you physically would never reverse the process. This is just kept as it is. Illuminated manuscripts are usually never touched, even if they're damaged. So what we have done here is creating, based also on another imaging, on another type of imaging data, which is called infrared imaging. We have looked underneath the skirt, kind of, and captured the structures from there and used them to propagate color values into the region of the skirt and then create this virtual kind of restoration of these illuminations. Another important topic that arises all the time in applications in biology and medicine related to imaging is motion estimation. You want to quantify motion that is happening in videos. And so this is an example of a Drosophila embryo where they are interested. I don't know, you might not even see a lot of movement here. It's an extremely noisy video. And so what they're interested in here is to quantify directionality of where things are moving, which is here given in this Rose diagram. So they want to know in which direction most of the guys are moving. And this is another type of variational approach that can solve this. Special effects in photographs. This is Joanna, a former PhD student of mine. And she has many talents, but in particular she's a great mathematician, but she can't fly. So this is really a special effect. She has been sitting on a stool, and this is the method that allows you to get rid of this stool and replace it by the background. It's called image inpainting. And that could be another variational approach, or associated to a variational approach. Very often people are looking at partial differential equations. in terms of the Euler-Lagrange equation that is associated to this variational approach. So there are lots of huge number of applications for which these variational regularization methods are used. Now, we've heard already in the morning, and we have heard about this in the last, I don't know, 5 years or so, this rise of another type of approach to image processing, which are deep neural networks. So here the idea is you don't start out with a model, or you start out with a highly over-parameterized model, and you are learning the model that should solve your task by looking at enough data, by looking at enough examples of the kind of things you want to achieve. And so this has been successfully applied to many, many different applications. Many of the things that I've shown you here could be solved by these type of techniques. But what we were interested in is, in particular, combining this power of deep neural networks and complement some things that are very challenging for us in these variational regularization approaches, complementing those, replacing those by deep neural networks. So this is the idea, and I'm going to motivate this now. I'm going to show you what we did. Okay. So this is joint work with Sebastian Lunz, who is a CCMI student. And let me already say now that this is really his work. It's really so the work that I'm going to show you, he did everything, basically. And a colleague of mine from KTH, Ozan Öktem. Okay, so again, back to our variational problem. This is the variational problem. I am fixing my data discrepancy term to just the least squares fit between the forward model and my measurements. And what I'm interested in now, looking at this, is this regularization term here. So in all these applications I've shown you, these regularization terms, like for instance the total variation, they are very handcrafted guys. So you try to design them in a way that encapsulates some of the structures you want to use, some of the structures you assume your solution has, and you try to formalize those and put them into this regularization term. And so I've shown you only the total variation as one example, but there are a huge number of such regularization terms based on wavelets, based on shearlets, all kinds of lets, based on higher order derivatives of your image, and so on. So these are handcrafted usually, and what I'm interested in now is to replace this regularization term, or to make this regularization term less handcrafted and more data-driven. And this will be now the term where I want to use deep neural networks as a parameterization, which is then adapted to particular examples. Okay, so this is the motivation. And I want to do it in this way. I don't want to go directly to a deep neural network and just forget all about this variational approach because of two reasons. One reason is that what I've said before, I'm in particular interested in examples where this forward operator T is complex. So I don't necessarily want to train my deep neural network to also learn how to invert this operator T. And another reason is that sticking to this variational approach, what I will show you in a couple of minutes, is that we can still prove things about a solution, really going back to very, very classical regularization analysis. Okay? Functional analysis, basically. So this is the idea. Now, how does this fit into the framework of what people have already tried with deep neural networks to solve such inverse problems? And so the first one is the thing that I just said we don't want to do, are fully learned models. We have played around with fully learned models a little bit, for instance, for one application that I'm going to show you, computer tomography. So in computer tomography, this forward operator T are line integrals through your image X that you want to retrieve. And the issue is, because if you do this fully learned and you don't actually tell the network what this forward operator is, this network also has to learn this, has to learn what the forward operator is and how to invert it. And so this means for these fully learned models, the difficulties are that you need a lot of training data to make them robust. And if you don't use a lot of data, they will hallucinate something. They will start to, if you just train them on a small training set that is very specific, if you then apply it to something even, still close to that, but a bit outside of it, they will start doing strange things. So this is very difficult to train them. Another approach that people have pursued, I would say starting kind of last year, was to say, okay, if my forward operator is so complex, let's just first invert in some way, using, for instance, the pseudo-inverse of this operator T. First invert in a very simple fashion this forward operator, and then use the neural network to clean up all the artifacts that have resulted from doing this in a crude fashion. Okay? So in CT, for instance, you could think that you first apply filtered back projection, then you are in your image space, and then you use a neural network to do the cleaning up. So this is what we call here post-processing. Another range of approaches that have been proposed in Ozan's group, again starting last year, were to still stick to the deep neural network architectures, but to encapsulate the knowledge about the forward operator by feeding also the forward operator into your input layer of these networks and doing this iteratively. So always reminding the network of what the measurements are. And so I call this here the iterative schemes. So again, we want to stick to this variational formulation. We want to parameterize not only the regularizer in a way, with the hope that we can actually prove something. And we can prove something. It's kind of weak what we can prove, but we can prove something at least. Okay, so again, a bit of motivation. So what we want to do is we want to design a regularization functional R that does not necessarily require the solution of the minimization problem to make things cheaper, but also to eventually decouple the regularization from the particular inverse problem you want to solve. And we want to do this using now this idea of generative adversarial networks, in particular the discriminator part, by training this regularizer to distinguish between the type of solutions, artifact-free images, ground truth images, let's say, that I want to retrieve, and images with artifacts, with typical types of artifacts that standard approaches would show you. For instance, you could think of these images, the bad images that you want to get far away from. You could think of those, for instance, as being created by applying the pseudo-inverse of your forward operator T to the typical types of measurements that you take. Okay, so you train this regularizer on two distributions, maximizing the distance between those two distributions. A distribution of good images you want to achieve and a distribution of bad images that you want to avoid. So this is somehow the idea. And I have here a little reference that goes back to a paper that we've written with Martin Benning, Joanna Gra, and Guy Gilboa, where on an extremely simplistic level we have tried to do something similar. At that point, actually, we didn't know anything about discriminators or generators or anything like that. What we did here was to mimic this, good and bad examples. What we did is we trained a regularizer to be very large for one type of images, the images that come from the bad image distribution, and very small for images that come from the good image distribution by minimizing a quotient of the two. Very simplistic, but, well, it also kind of worked, but this was the kind of shallow approach to doing something like that. Okay, so let's go on with what we want to do. So again, we have this variational approach here. And what we want to do is we want to replace this regularizer now by some parameterized guy, psi theta, where these parameters are trained on undesirable and desirable examples that I'm feeding it with. And I want to do this in this form here by minimizing a loss function of that type, where you are maximizing the distance between the answer of this regularizer for images coming from the good distribution and the answer this regularizer gives on average coming from the distribution of the bad images. Okay? So what particular type of this distance did we choose? So we looked into doing this via Wasserstein loss, which is again motivated by a recent contribution on Wasserstein GANs. So here we look. Let's start here. We look at the dual formulation of the Wasserstein distance, and we look for a regularizer f that maximizes this difference. So this is somehow the idea. And what you see here on top is an approximation of this Wasserstein distance, where you're looking for one Lipschitz f by adding this one Lipschitz constraint as a penalty to the energy. Okay? So this is an approximation. We just choose a finite lambda in order to enforce this. Okay, so this is the idea. Now, does this make sense? So you might want to do a first sanity check. Does this such a regularizer make sense at all? And so one of the things you might think of doing, of checking, is the following. If you look at a sample, an image sampled from the bad image distribution, and then you create a new sample, G epsilon, by going into the negative direction of the gradient of this regularizer, right? You do a gradient descent on the regularizer. What you would hope is that, and you do this for a lot of samples coming from rho, what you hope is that this new distribution that is now built up from these slightly decreased, from these samples that have a slightly decreased such regularizer, what you would hope is that this new distribution is closer to the distribution of the good images, the desirable ones that you want to achieve. And this is indeed a case. It's a very simple thing. But what you can show is that under sufficient regularity assumption that I'm happy to go into later on, if you take, if you look at the Wasserstein distance between this distribution rho epsilon and the good distribution, this is really decreasing. Okay? When you take this step in the negative gradient direction of the regularizer. Okay, so this is the first sanity check. Seems to be kind of what you might want from such a regularizer, because you, in the end, you're putting this into this variational problem and you're minimizing it, right? Another thing is to get a bit of an intuition what it means that we are training a regularizer to distinguish between the good and the bad images. And so what ideally you would want is that this regularizer resembles some kind of distance function to the desirable images. So it learns to distinguish between the bad and the good images by, in the limit case, being a distance function to the data manifold being the manifold of the desirable solutions. And so this is a typical type of assumption that is being taken in these GAN papers, which is the data manifold assumption, which just means that the support of the distribution of your good images is weakly compact. Okay. So what can we show in this case? Is this actually really a distance function? And so what you can show is if, and this is now an assumption that tells you that the distribution of the bad and the distribution of the good images is close enough together such that you can achieve one by the other by a projection. So you can take the distribution of bad images and project them onto the distribution of good images. And if this is the case, so you're not completely off, you can still see some resemblance. Let's say this is kind of heuristic, right? How you check that actually. It's hard to check that. But if you have this, then you can indeed show that the maximizer, this f that is maximizing this, which is my regularizer, is indeed given by the distance function to the data manifold. So it's indeed doing what we have set out, what we set out that it should do. How do you do this now? Just to give you an overview. So what do you do practically? So you have this loss function. Now I've written it down in a finite dimensional case. You feed it with examples of good images and examples of bad images. And the bad images, if your forward operator T is a pseudo-inverse, you could just take the pseudo-inverse applied to the data as your bad images. And then you minimize this loss function with respect to theta. You compute n optimal theta, and then you take this psi theta and put it into this variational regularization approach, and then you solve this for whatever new data that you get. Okay. One quick word is that we are not learning this weight in front of the regularizer, but we are just looking at examples where we can actually estimate it. So there are various ways how you can estimate this weight lambda, and we have chosen one. So, okay, then you solve this variational problem with whichever method you want. We have just chosen gradient descent as a very first simple approach to solve this then. Okay. Now, I said at the beginning we want to stick to this variational problem because we want to be able to prove some stability properties of the solution. And so this is something we can indeed do, at least stability in a weak sense, in the following way. What you need are two ingredients, or the main ingredient that you need in order to prove stability is this coercivity here, which means that if the solution x goes in norm to infinity, then also the functional goes to infinity. And so in order to ensure this, you can decide upon two properties that might fit your application, your inverse problem you want to solve. Either you assume enough continuity on the forward operator T in order to ensure this, or you assume that the regularizer is coercive, and you can assume this, but you can also trigger this through the training. And the particular way how you can trigger this through the training is a recursive training approach, where basically where you prevent this regularizer to be unbounded from below. You want it to be bounded from below in order to ensure this. And the recursive training means that you are you start out with bad and good examples, you train your psi theta, you solve the variational problem, and then you update your distribution of the bad examples with the solutions of the variational problem. So you do this recursively. Okay, so under these assumptions, first of all, you can prove that a solution exists to this variational approach. And then you can prove stability in the sense that if you start out with a sequence of measurements yn that converge in norm to a measurement y, and you look at the corresponding sequence of minimizers that I call xn, then this sequence xn has a weakly convergent subsequence which converges to a solution for the limiting measurement. Okay? Let me say that at the moment I think there is not so much more hope to prove more than this type of stability. The regularizer is non-convex. It's very non-convex, and that's, you know, that's the price we pay by making this a bit more data-driven. Okay, let me skip this. I kind of said this already. So how you train this is that you compute, that you train the regularizer psi theta on these good and bad examples. You might do recursive training if you need to. And let me also say one quick word, the psi theta, actually we didn't put a lot of engineering into this psi theta. We just used an off-the-shelf network for classification. Okay, so some results. So there are two kind of test cases that we have tried. One of them is CT, computed tomography. As I said, this is the case when the measurements y are line integrals of an image that you want to retrieve. In this case, we have undersampled in measurement space 4 times. So 4 times undersampling, and we've put some noise onto the measurements, some normally distributed noise. And what you see here, going from left to right, is the following comparison. So this is simulated. It uses the so-called lunar data set, which is a data set of lungs that have lesions in them, cancerous lesions. And so what we did here is, so this is the ground truth, the CT ground truth image. This is now, I'm not showing you the sinograms. I'm going to show you the actual measurements in a few seconds. This is the kind of very simplest solution that you might think of, just applying the pseudo-inverse. This is the filtered back projection applied to this noisy undersampled data. So these will be our negative examples. This here is solving this with the total variation regularization. Okay, so this regularizer, which has been around for ages in the imaging community very successfully. This here is the result when you do this post-processing. So you first invert, and then you send your images. So these guys here through a neural network to clean up the artifacts. And this is the one that comes out from this deep regularizer, this adversarial regularizer. So let's look a little bit more into the details. Just going through here the following. This is the ground truth. This is the adversarial regularizer result. This compared is the bad image, the filtered back projection one. This is the TV regularizer, which has been really a gold standard for solving these CT problems until now. And this is what you get via post-processing. So first inverting and then cleaning up. So what you can see a little bit is that, although on the next slide I will show you that the post-processing is on average, in terms of quality measures, still doing slightly better than this adversarial regularizer. You can see that a few of the finer details are actually coming up nicely in this adversarial example. So visually, as a first inspection, this might seem promising. So this is quality measures on the output, comparing these different methods. Let me say one more thing. I'm calling this adversarial regularizer unsupervised because you don't have you train it offline. You don't need to have so you don't need to train it on paired examples. So since this loss function is actually measuring the distance between distribution of images, your good and bad examples don't even have to be paired to each other, which is very attractive for lots of inverse imaging applications, because a lot of times you don't have ground truth images for the type of measurements that you take. Yeah? So you don't need this for the adversarial regularizer. Let me jump over this. This is, by the way, the measurements. These are the Y's that we are starting out with. And so you can imagine if you would fully learn this, if you would just put this into a neural network and want that something like this comes out, it's a very challenging task. You can do it, yeah, but I haven't seen anyone who has done this successfully. You would need such a large training set that I think this is really unfeasible. Okay, so we can do this for denoising, but it's not so interesting. The forward operator T in this case is actually quite simple. But let me just turn to the takeaway messages. So what have we done? We have proposed a Wasserstein gun regularizer for solving these inverse imaging problems, training this regularizer on these desirable and undesirable examples. Some of the advantages is that we are sticking to the discrepancy term. We are sticking to the forward model. This is very directly inserted into the variational model. We can derive some guarantees on the solution, like stability. And one thing that I didn't have time to go too much into, but the really cool thing about this is, and I think that's why we really need to push this more into actual applications, not just on these simulations, is that you don't need paired training data. And that's really a crucial thing in lots of these physics-based imaging inverse problems where you just don't have the ground truth. So replacing this ground truth by some other examples that you have is very interesting. And another thing is that you don't need a lot of examples to train them. I can give you more concrete quantities on how much you need, but you need significantly less than in the supervised case where you just do this post-processing, which is another advantage. The disadvantage, and I mean I've listed now one, but this is a crucial one of course, is that the computational complexity is still you need to solve this variational problem. And this has also been one of the motivations, I would say, for people looking into these deep neural networks, because these variational problems, although they have been around for such a long time, they are very heavy to solve computationally. So we still need to do that, okay? So that's maybe the biggest disadvantage. And the overall philosophy is to use ideas from machine learning, like deep neural networks, in more structured approaches where you can still take advantage of modeling information you have, for instance, about where these measurements come from. And with that, I thank you very much for your attention.
Time, but we have already time for one question. So,
yes.
Yeah,
how do these ideas compare to something like non-local or BM3D regularizer on
Yeah, so we haven't really compared with, for instance, BM3D because it was not designed to solve in particular denoising or something like this. It was just
I was thinking the CT, right? The inverse problem.
Yeah, also cleaning up with BM3D afterwards, after the inversion.
As a like the non-local, like just non-local means, right? As a regularizer for, right?
Yeah, we haven't compared. So we have compared with TV.
That's sort of like using the, the idea there is you're sort of like using the noisy, like you use a filtered back projection, for example,
and then
noisy
clean
data,
it up,
right, as like prior, right, for the for that non-local means filter. I mean, it's not the same thing. You're not using auxiliary data at all, but.
So I think that could be interesting. I think the main difference here really is that you're making this regularizer more data driven. So this is the thing. With a non-local regularizer, it's true. So you're looking at statistics in a more global fashion on the image, but you're just using this one image. So that's why we compared more with these more data-driven types of regularization.
Not a criticism of the method. I was just curious.
We did not. We did not compare it.
Okay.
Well, in the interest of time, let us thank Carola again. We'll have